with 6 zeros on it, and then I'll run for 100 iterations. And then here I've just defined an instance of my function using this bisection square root that I defined up here, and then plug the iterations. So we have the approximate square root for the first iteration, wasn't really great, 7.5, 1.5, way off. And then as we go through each iteration, you can see that the absolute error and the relative error are getting smaller, right? And what we'd like is if it was 0, but since we're dealing with computers, we probably can't get a perfect 0. And you can see at the 24th iteration, we had actually gotten our absolute error smaller than our tolerance, and we had a prediction that the square root of 25 is 4.99999, you know, a lot of nines and some other numbers, which is basically 5. And yeah, we were less than the tolerance, so it converged. So it approximates that the square root of 25 is about 5, which is a good guess. Let's see. Okay, so here's another example. Same idea. I'm running through here, but this is just a custom polynomial. You know, we might want to find the zeros of polynomials. We all know the quadratic formula, and maybe some of you know the cubic formula, which is pretty monstrous. But this is just a way to find higher degree polynomials. And it's just the same thing. You know, we have our C, we have our FC, just defining our function here, evaluating an at C. We want to find our zeros, have our absolute error, relative error, and our iterations. So same thing, I just changed the function here. And then I have a small example use that we can do here. Set A equals to 1, B equals to 3. I set my tolerance, my max iterations, and then I've defined an instance of my function to see what happens. All right, so same thing, we can see that the error is going down, decreasing here, but the relative error is staying the same. And when we get to the end here, we have an approximate root of 3, right, and an absolute error, very, very small. So it guesses that 3 is a root of this polynomial. And that makes sense with this final term here, right? 3 is a factor of 3. And if you figure this out, then you'll see that 3 is a root. So it's a way that you can use the bisection method to find roots of polynomials as well. And then since that was a degree 3, you could of course use a division algorithm that, you know, divide out the root, and then you would have a quadratic, and then you could find all of the roots in that way. Okay, the next thing that I want to talk about is the fixed point iteration method. So the fixed point iteration method is a numerical technique that we use to find the root of a real valued function, again real valued, by transforming the root finding problem into an equivalent fixed point problem. So it relies on finding a fixed point iteration function such that g of x is x. So you can see that if we can find g of x equal to x, then that's the same thing as finding g of x minus x equal to 0, right? So we've transformed a root finding problem into an equivalent fixed point problem. That's what that means. This method is iterative, so it relies on, you know, reapplying it to himself over and over and over, and it converges to the root if certain conditions are met. One of those conditions that you might see, you may have already seen, you may see later in your math careers, is if we have a contraction, right? So that's actually something you could prove in a sort of real analysis course. And let me just go through the algorithm here. So typically it's implemented using this algorithm or some kind of variation. We choose an initial guess close to the desired solution. we set a tolerance level to determine how accurate we want it to be. And for each iteration k, so k would be the x. So if this was xk, this would be xk plus 1, and then each iteration would be plugging this back in to g. So it's a repeated composition, as we'll see here in these notes. So for each iteration k equals 0, 1, 2, we repeat the following steps until we get convergence. So we want to calculate the next approximation, xk plus 1, by using this formula. So like I said, we just plug in xk into our function g, and that tells us what xk plus 1 is. After that, we'll calculate the absolute error. So how far is xk plus 1 from xk? And we can calculate the relative error as well. And then we can check convergence, right? So it's the same idea as before. If the absolute error or the relative error is below our tolerance epsilon, or if the max number of iterations is reached, we'll stop. Otherwise, we just do the next iteration. Xk plus 2 would be g of xk plus 1. Then xk plus 3 would be g of xk plus 2. I think you get the idea. And once these conditions are met, our convergence check, the final xk is the approximate solution to the equation f of x equals 0. In this case, our f of x was g of x minus x, right? So that brings it around full circle. All right, so just to have a little discussion about this, some ideas that you could take home with you. The fixed point iteration is an iterative process, and it may converge to a solution when certain conditions are met. So the function should be continuous on the interval of interest, right? And the fixed point should be within the interval AB, where A and B are the initial guess and the value obtained after the first iteration respectively. So that means A is your initial guess, B is the value you get after the very first iteration, and the fixed point should be somewhere between those two numbers. We need to choose our G appropriately so that we can have convergence. So, certain types of functions won't converge, and for other types of functions, it may converge very slowly or may diverge if we don't choose properly. So we have to be a little mindful of when we're doing that. So this algorithm is used in solving nonlinear equations, optimization problems, and other mathematical computations. However, it requires careful selection of G and initial guess to ensure convergence. Again, so we have to really think about this G in order to get convergence. But it's very useful. It's good for nonlinears, optimizations, and other types, as we'll see. The error analysis. So how do we assess the accuracy of our method? Well, again, we can analyze the errors, right? Just like we did before, we had the absolute error along with the relative error, and that gives us a way to analyze. Commonly used error analysis methods include observing how the error decreases with each iteration and comparing it to a predefined tolerance. So we set some kind of tolerance for our error, just like we did before. When it's smaller than that tolerance, we'll go ahead and say the algorithm converged. Okay, so I'll do one little example here for you. I've written up a function here. This is a fixed point iteration to find, square root. So I have an input x here, an initial guess, a tolerance, and a max number of iterations. I call guess the initial guess, and for I in range max iterations, I'll take 0.5 times our guess plus x divided by our guess. So this is the fixed point iteration function for square root of x. It's a pretty classical function. So one thing to note is that this number here is less than 1. in the front here. So that's just something to think about. Like, what would happen if I changed it, right? I've defined my absolute error. I've defined the relative error, and then just printed a little for a loop to give us the iterations, the approximate square root, and then the absolute error, the relative error. And if the absolute error is less than the tolerance, then I'll say my algorithm converged, and I'll break my for loop. And then at the end, we'll return that guess, right? So that guess, you can see it depends on itself. So it's updating itself. That's the idea of iteration. That's why it's called the fixed point iteration method. Okay, so we can define this function, and then just look at a little example usage here. All right, so I'm going to, again, use the square root of 25, which is easy to determine. The initial guess is, well, let's change this. Let's say 4. And then I have my tolerance and my max iterations, and then I just call an instance of the function. So since my initial guess was pretty close to the actual guess, it only took me 3 iterations to get that level of precision that I wanted. And as you can see, the absolute error again was decreasing. We have the e to the -7 here, so that's like 7 zeros. And then once it got below that error that I chose of 1 e to the -6, we said it converged. All right, let me just pause for a second and make sure there's no questions. So let me check the chat. Let's see. All right, so far so good. Let's go ahead and continue. All right, now I don't want to do just these kind of boring examples for you that are, just find the square root of 25. Everybody knows that. It's kind of not that interesting. So I want to show you something that's really interesting that uses fixed point iteration. So this is the idea of fractals. So maybe you've seen these before, like if you read about different kind of math concepts. And this is a fractal called the Julia set, and it's generated using fixed point iteration. So this is a set of complex numbers. And then when we iteratively transform them, the set either remains bounded or it just blows up to infinity. And the fractal is created by examining the behavior of these iterations for different initial complex numbers. And so we're looking at an iterative fixed point method, but for complex numbers. And I'll show you how we can kind of go through that. So at the heart of the Julia fractal is the concept of fixed point iteration. So this is our iterative numerical method, and we want to find a value x such that f of x is equal to x, but we're going to do it with the complex, right? So we start with an initial complex number, z0, and then iteratively apply a function. We keep doing the same thing, but now we're dealing with complex numbers, so it'll be a complex function. So f of z0 would be z1. F of z1 would be z2, same idea. So we'll keep doing this for a maximum number of iterations or until our complex number is bigger than a certain threshold, right? It'll stop. And the key is to choose a function that results in interesting and visually appealing patterns when we iterate. So the Julia set is one such interesting function, and we start with an initial complex number z0. I don't know why that. Let's see. Okay, that's fine. And sorry about that. And what we have as our function is f of z is z squared plus c for some complex constant. So I've written it down here, and this would be our function f over here. So zn plus 1 is zn squared plus c. We'll repeat this for a maximum number of iterations or until the norm of zn or the absolute value of zn exceeds a threshold. If this is bounded for all iterations, then Z0 is part of the Julia set. Otherwise, it's not. It's not in the set. So that's a nice sort of idea you can play around with mathematically. And by experimenting with different values of C and the grid of initial complex numbers, so which complex numbers you choose, you can get a lot of different interesting fractals using this idea. So I've written a little code here for you to show you kind of what's going on. Now there's a lot to this. It has a width, a height, an x-min, an x-max, a y-min, and a y-max. And so basically I'm representing my complex numbers here by R2, the plane, and my width and height is the box within that I want to look at that those complex numbers lie. So x-min could also be, the real part of a complex number. Y-min would be the imaginary part. And then the same for x-max and y-max. And then I have a C here, right? That was my parameter in the definition here. So that's the C here. And then I have some max iterations here. So my x values I want to take within my grid of complex numbers, the x-axis or the real axis of some width. And then as for my y values, I want to take all of their imaginary parts within some height. So you can imagine a square in the complex plane, or in this case, we're kind of using what's called the isomorphism between the complex numbers and the real plane. I don't know if you know that word yet or not, but the idea is that I'm just building a grid in the plane and I have a bunch of numbers in that grid that I'm using, and we're thinking of those instead of ordered pairs like x comma y, we're thinking of them as the real part and the imaginary part. Okay, and then my fractal, I'll just initialize my grid with the zeros of some width and some height. And then here's the actual iteration part. For x in the range of my width, for y in the range of my height, my new zx and my new zy will be my x values, which is this list applied to the x. So this will go through, 0 to however wide I make this. And this one will go from 0 to however tall I make this. So it'll start at the 0 index for width and the 0 index for height. And then it'll go to the 1, the 2, the 2, right? And it'll update. I initialize my iteration at 0. And then I use this bound here. So whenever zx squared plus zy squared is less than 4, if you remember from your calculus class, this is a norm, right? Or a dot product, the length of a vector, x squared plus y squared, the most famous, of course, is x squared plus y squared is 1. So, or less than 1, which would either be the circle itself if it's equal to 1. If it's less than 1, it's the inside of the circle, the disk. In this case, I have 4. So whenever the length is less than 4 and my iteration is less than my max iteration, well, then I update, right? So I have my x temp is my x squared minus my y squared plus a real number c. And then my z at y zx gets updated to be twice that plus c, the imaginary part of c, and then x temp, and then I just add 1 to my iteration. And my actual fractal on x comma y will be my iteration divided by my max iterations. All right, so that's the function that we get. And we can set some parameters. So in this case, I've done 800 by 800. So you can imagine 800 integers along the x-axis would be the width. 800 integers along the y-axis would be the height. And then my x-min and x-min would be -2, 2, the same for my y. For c, I've just grabbed this complex number here. The real part is 0.355. And so is the imaginary part. We can change this C to just explore different types of Julia sets. And then I've generated my Julia fractal into this list, which returns the fractal. And these are the parameters for my function. And then down here, I've just typed a little code because it's interesting to talk about all this code and what's going on, but it's really cool to see it. So let's go ahead and run this and see what one might look like. Might take a few seconds, but that's okay. There we go. So there is the Julia set fractal using those parameters that I defined there. So you can see it's really kind of beautiful and interesting, and it has this repeating fractal property. As you zoom in, they're all kind of copies of themselves. And this is the kind of interesting stuff you can get with using fixed point iteration ideas that converge to some kind of a point. All right, so skip these little. So here I've just written out a fixed point iteration custom function. Again, this is a polynomial. We want to find the roots. So I have a guess here for what they could be. And then I have my custom function here. So this is my fixed point iteration function for my custom function. And this is the actual one. I have the absolute error, the relative error, and then I printed out, what these will be for each approximation. So this is another example of what we can do. And then I'll just show you an instance of this function as well. All right, so in this case, we had 10 iterations. I don't believe the errors got below the tolerance here. This one, if you set like 100, I believe it diverges off, so it doesn't, or no, it actually truncates. Okay, so yeah, it just takes a lot to actually get this, but this is another algorithm you can use to find roots. It's, a little bit, it's kind of interesting because we have a guess function here. This is my fixed point iteration function that I'm going to use for my custom function. And you can see if you play around with these two functions and subtract them from each other, why this is a good one to use for this function. So I'll let you, write that down and think about that. And that gives you a way to look at these things using fixed point iteration. Okay. All right, let's check the chat again before we move on, just to see if there's any questions. Okay, so hopefully everybody's following along okay. If I'm going too fast or if you have any questions, just put them in the chat here, or even just speak out loud, it's fine, but just let me know. Okay, so we've talked about the bisection method and we've talked about the fixed point iteration. Now we're going to start talking about some matrix type numerical techniques that we can use, because in the real world, a lot of problems aren't just one variable, right? They're multiple variable problems, so matrices are involved, and that allows us to solve different types of equations. The first one we want to talk about is LU factorization. So this stands for lower upper factorization. And this is a technique that we can use to decompose a square matrix into a product of matrices, right? One lower and one upper. This decomposition simplifies the process of solving linear systems of equations, because a lower triangular and a upper triangular matrix have really beautiful properties, and they're way easier to use than just an arbitrary square matrix, right? So that's something to think about. And this is used in a lot of numerical methods as well. So let's go through how this works. So first we decompose our matrix A into lower and upper triangular. So the A is equal to L times U. And then we'll perform a forward substitution to solve the equation Ly equal to B for some y, and then a back substitution to solve Ux equals y for x. And also I want to go through the actual decomposition algorithm just so that you have, you have a reference for that. So the input for this would be a square matrix A of size n by n. And then the output would be lower triangular and upper triangular such that A is LU. And how do we do this? So start with your matrix A, and then in whatever coding language you like to use, you can create two empty matrices, L and U, that have the same size as A. So for each row I from 1 to n inclusive, set the diagonal element of L equal to 1. For each column J from I to n exclusive, calculate the value of Uij using this formula. So Uij will be Aij minus the sum from k equals 1 to I minus 1 of Lik Ukj. And for each row k from I plus 1 to n inclusive, we can calculate the value of Lki using the formula Lki is 1 over Uii times Aki minus the sum from j equals 1 to I minus 1 of Lkj to Uji. So when this indexing notation I'm using, you can think of just like a regular matrix for rows and columns. And then the summation just says start at, in this case, column 1. So, and then go up to column I minus 1. So we would be summing over the columns here because you can see the J here, the J here. And then over here, we're summing over the columns in the first, in this one, it would be the columns and the rows, and then the same sort of thing here. The columns here, and then the rows. And this, the first entry is the rows, the second entry is the columns, and then we sum over J. After the factorization is complete, you will now have a lower triangular matrix, L, and an upper triangular matrix, U, such that A is LU. This is a good method for scientific computing to solve linear systems and to do different matrix operations, and it simplifies the process of linear equations. And again, we can look at the errors by comparing the exact solution to the computed solution using our absolute and relative errors. Okay, and to give you an algorithm for this, I've basically taken that algorithm that I just explained and written it into a function. So again, this takes in a matrix A, and then I'll call N my shape, and then I make two empty matrices of size n by n, right? So A is going to be square, shape 0 will be the first n. So actually the shape of A is n by n, but I'm just taking the first dimension of A. So that's my n, and then these are n by n. And then for I in range n, we make our lower diagonal, the II, right? Row I, column I, that's the diagonal, equals to 1. And then for J in range IN, right? So that's my columns I was talking about. We use those formulas that we had up there. So Uij is Aij minus the sum of this product for k in range I, right? So the column here, the row here. And then for j in range I plus 1 to n, Lji is Aj minus the sum for k in range I, right? Again, we have the column here, the row here, and then I divide that by Uii. So this is the exact algorithm that I showed you here. I've just implemented it in Python here. And then I want to return L and U. Okay. Okay, so this is an algorithm that I made to solve a linear equation, or linear system rather. So this takes as a matrix A, and then the classic linear equation that you have from, if I don't know a book you guys use, but solve for x, it looks something like this, right? Ax equal to b, and that's the idea here. This is the A, this is the b, and we want to find the x's. There could be none, there could be infinitely many, there could be unique x that works. So LU, I'll implement my LU factorization function, which is right here. So that gives me my L and my U. And then again, I take my dimension of A, which is square, right? So the row dimension and the column dimension are the same. And then I forward substitute to solve Ly equal to B, as I was talking about in the algorithm earlier. So I make a y vector of zeros of size n. And for I in that range, my yi will be bi minus the sum of the Lij times yj for j in range I. And then I'll back substitute those in once I've solved this to solve ux equal to y. So again, my x will be a zero vector, and then I'll populate or fill in the zeros with this expression here for the range n-1 in backward steps. So that's what these negative ones are. It'll go down to -1 and negative backward steps of size 1. And then I've indexed it here by I, yi minus the sum of the uij times xj for j in range I plus 1 to n, and then divide by the uii. So that'll solve the system. And I return x, right? That was what I was trying to solve for, is x. And just to show you how these work, so I've created a square matrix here. 2, -1, 1 would be the first row. Second would be -1, 3, -2, the second row. And then the third would be 1, -2, 4. So this is a 3 by 3. Here is a vector b. But first, I just want to show you how the LU factorization works. So I have my LU from my LU factorization function, and then I'm multiplying them there. So I should get A back if I did it correctly. So let's see. All right, so we have 2, -1, 1. That looks good. -1, 3, -2. All right. And 1, -2, 4. So I got the original matrix back when I multiplied those. And now I want to solve my system. It's just the same one. I just copied it down here. But now I'm going to use my other function to solve a system. And I'll print whatever the solution is. Okay, so it says 1.923 na 2.230 na and 2.384 na. So that's my solution. Is that correct? I don't know. But what I'll do is take this x, multiply it by a, and see if it gives me the same thing as b. So the first line here is a times x. The second line is b. And if you check, yeah, it gives us the same thing, right? The difference is one is in a float data type, 4 point, 0 point, 7 point. The other is integer. That's what that little decimal is there. But these are the same vector. All right, let me show you another example. I'll show you a couple more. So let's just think about this system of linear equations. You've probably seen 100 of these in your linear algebra course. So you're probably used to seeing these all the time. So I have 2x plus 3y minus z is 1. 4x plus 7y plus 3z is 2. And 6x plus 10y plus 5z is 3. If you recall, we can represent this system as a form ax equal to b. So I'll take a, and all I'm doing is I'm taking, for my first column, that'll be my x's. My second column, that'll be my y's. My third column, that'll be my z's. So you can see that 2x in the first equation, 4x in the second equation, 6x in the third equation, 2, 4, 6. For the y's, I have 3y. 7y, 10y, and in my matrix I have 3, 7, 10. And for my z's I have -1, 3, 5, and down here I have -1, 3, 5. So this will be my A, and I want to find all ordered triples or all triples x, y, z that solve this system. Well, here's my B, 1, 2, 3. You know, and you could do some things. You could find like the determinant of A to see if it has a unique solution or if it has many solutions or whatever. But we're not going to get into that at this moment. That's all stuff you know from linear algebra. What we will do is use LU composition, decomposition to find the solutions. So let's see if we can find them. Now in this little bit of code, I'm not using my functions that I wrote. I'm using some of the libraries in Python just to give you two different ways to look at it, right? And this you can see is a lot less code, but it works just as well. Okay, so here's my matrix, the 2, 3, -1, 4, 7, 3, 6, 10, 5. This one here, A. My B was 1, 2, 3. So that's the same B I have here. And then I'm going to use my LU decomposition using this SciPy library, right? This is a scientific computing library. So my L and pivot are going to be the LU factor on A, and then I'm going to use LU solve. So I've imported two functions here, LU factor, LU solve. And basically what this is doing is it's factorizing my A into L and U in the pivot column, and then it's actually solving it by plugging those in and then solving for B. And then I'll print whatever my solutions are. Okay, so I get 0.50 and -0, which is just 0. And let's just check if we get the same thing back. Yeah, when I multiply A times that X vector, I get 1, 2, 3, and my B was also 1, 2, 3. So we see that we get the correct solution in this case. Okay, so now I want to go through, like, why do we care about this? You know, like, we're learning these algorithms. They're interesting for their own sake, but some of this stuff shows up in the real world, and one day you might have a job and you might have to solve a problem and you might have to implement these algorithms. And a common one that shows up is in image processing, and the problem would be image deblurring. So if we have an original image from a blurred image or a degraded image, you know, let's say that somebody robbed a bank and the image is blurry, and you want to get rid of the blur and see their face more clearly so that they can be arrested, right? Something like that. So image blurring is often modeled as a convolution operation with what's called a blurring kernel. So that I wouldn't worry too much about, but that's going to be the place of some of the different vectors we're using. To deblur the image, we can represent the convolution as a linear system. That's what's important, right? So we have convolution is the linear system, and then use LU decomposition to get back the original image. So let's look at a simple example that I just kind of created myself. Yeah, let's just look at the actual example. Well, okay, let me talk about it a little. So we start with a blurred image, which is just a 2D array. So just a n by n matrix, just like we would do. And then we'll have a blurring kernel. And this will be the convolution operation. And usually this is known beforehand or is estimated. So there's a lot of these different convolution operations that you can learn about, and there's very common ones that you would use. So what we want to do is start with a linear system using this data, the blurred image and the blurred kernel. So we'll represent a linear system, or we'll define a linear system to represent the deblurring process. And every equation in our system of linear equation is going to correspond to some pixel in the deblurred image, or the blurred image. So we'll apply our LU decomposition on the coefficient matrix to get our lower and upper matrices. We'll do our forward and back substitution to solve our linear system, and we'll display the results. So, so here we have just some original image. I've taken some random numbers between 10 and 10, and then I have my set blurring kernel here. You can look, if you want to learn more about this on your own time, you can look at convolutions. And then I have my blurred image, right? So I'm using the convolution with my original image, the blurred kernel, and then I have some different parameters here that I've set: mode, same, boundary, wrap. Okay, so I'm sorry. We have a question. Yeah. Yes. Yes, I did. It's in the some files last week. So yeah, I'll send some after this lesson as well. All right, so this basically is the A in this case is constructed, and it's a result of the convolution between the identity and the blurring kernel. And this represents the relationship between the original image and the blurred image. So that's going to be my matrix A. And essentially, you can see it's nearly the same thing here, but I'm using the identity here, right, instead of the original image. And then I'm going to take this blur image and turn it into a vector. So now I have an A and a B, and I'm going to solve this. Again, I'm using the LU decomposition from the scientific library, and I want to solve my deblurred image to be, A, which X is equal to Y, and then reshape that to be the same size as my original image. And then this is just some code that I put in here to actually show the images and show how the process works, right? So let's go ahead and run these and make sure that they look okay. Okay, so you can see here that we have the original image, which is, what the image we're trying to get to, and then we have the blurred image. And then using the deblur, we see that it's not perfect, but we've solved the equations using LU decomposition. We've gotten the deblurred image, which is the solutions, and that's our approximation to this original image. So that's one way that you can use these ideas in the real world instead of just calculating things and looking at different things and wondering what's going on. Okay, let's go ahead and take a little break for now, and I will go ahead and when we get back, we'll do the next portion of the lesson. All right, let's go ahead and get back started. This question. Yeah, I'm in the U.S. right now, so actually for me it is 10:54 p.m. So yeah, I'm on the other side of the world. I'll wait a couple minutes for everyone to get back, or just at least 1 minute. Thanks for the question. And then we'll get started with the next materials. Good morning to you. Thank you for the comment. All right, let's go ahead and get started with a few more ideas. We've talked about some algorithms. And also, if there's anything you want me to go over again, like you didn't follow it all the way, just let me know, and I'll check in periodically. I'll check the chat to make sure we're doing okay. Okay, so the next thing after our real world example of LU decomposition, we want to talk about the norms of vectors and matrices, right? And probably you've seen this kind of stuff, but it's good to kind of get a good idea of how vast it is. There's a lot to it that you probably haven't seen. So the idea is that in linear algebra, norms are mathematical functions that somehow measure the size or the magnitude of vectors and matrices, right? So the very first one you learned was the absolute value, right? It tells you how far is a number from zero. It gives its size. And that idea is kind of being generalized here. And that's what we're going to look at. So these provide a way to quantify distance or size of mathematical objects in a vector space. Norms are crucial in various mathematical and engineering fields, including machine learning and optimization. So if you want to do any of these two fields in the real world, you'll have to learn about norms and understand them, especially optimization. Okay, so let's talk about some different types of norms. Let's start with vector norms. So you've probably seen this in like your calculus class. A vector norm denoted usually with double brackets, where x is a vector, is a function that maps a vector to any non-negative real number. So this is just like with the absolute value, it cannot be negative. Right, it has to map to a negative or a non-negative real number, and there's several common norms, vector norms, and the one that you'll see most widely is the LP norm, right? So in machine learning, you would use this LP norm to help when you're trying to optimize your function. You would use it to like give a different weight to what's called your loss function. So maybe you have two classes of objects, cats and dogs, but you have like 100 pictures of cats and maybe just 10 pictures of dogs. You could use different types of LP norms to give a weight to that smaller number of dogs, and then it would help the machine learning model understand it better, because it would use that weight to penalize different predictions and different errors. And then that way you don't have to worry about weird things happening in your algorithm. So these do come in handy. The first class of norms that we want to talk about are the LP norms. So the LP norm of a vector in any n-dimensional space is defined like this. So usually it'll be a double bracket with a lowercase p, and then what we're doing is we're taking the sum over all of the components of the vector. So if x is the vector, these are the components of the vector, x1, x2, x3, all the way up to xn. And we want to sum all those up, take their absolute value to the power p, and sum that up rather. And then on top of that, we want to take that to the 1 over p power. So if you stare at this for a little while, then you'll start to kind of see that actually this isn't that crazy. You've seen this before. And actually, we've even seen it in tonight's lesson or today's lesson. When p is 2, it's known as the Euclidean norm or 2 norm. So I have a 2 here, and then I would take the sum of all of the components of my vector square the square root. Well, we've seen that, right? That's the square root of the sum of the squares of the vector. That's the one you know from, multi-dimensional calculus or linear algebra. You've seen that. But it doesn't just have to be 2. If it's 1, well, then 1 over 1 is just 1, and we're just taking the sums of the absolute values. And this is called what's sometimes called the Manhattan norm or the 1 norm, right? So they have different kind of properties. When you have the L2 norm, it's really special. Like I won't go into that, but there's something special about, if you have a space and it has the L2 norm, there's something special about that space, the L2 space of functions. But it doesn't have to be 2 or 1 either, right? It can be any values of p that are integer values. So you could even have, 3 or 4, whatever you want. So you could play around with these different norms. And one kind of fun thing to do if you're interested is when it's 2 and you set it equal to 1, then you would get a circle, right? Like, x squared plus y squared is equal to 1, or you'd get a sphere depending. Well, try setting it to different numbers and see what you would get if you set it equal to 1. Maybe you'll get different shapes and things like that. So that's kind of a fun little exercise that you can do. The next one is the infinity norm or the L infinity norm. And this one's really useful when you get into a higher level analysis. You'll see this come up a lot. It has a relationship to these p norms. And these are all, there's a lot of interesting things you can say. The infinity norm of a vector x is the maximum absolute element in the vector. So what does that mean? Well, if my vector x is, if I think of it as x1, x2, x3, then the infinity norm will be the maximum one. So like if it was 1, 2, 3, well, then the maximum xi would just be 3 in that case. If it was 1/2, 1/3, 1/8, the maximum would be 1/2. So it's just denoted by double brackets x with an inf, and it'll be equal to the maximum element of the norm. The inf should be an infinity. That's a typo there. Let me, I guess, okay. Okay, I guess. So yeah, the maximum element, that's the infinity norm. So how do we actually define these norms? Well, they follow a set of axioms or properties. So in order for it to be a norm, it's just like to be, if you've learned about metrics have their own properties. Well, so do norms, right? So they have to satisfy the following properties for all vectors x and y and scalars c. Now, why do we want to talk about vectors and scalars? Because remember, a vector space is a subspace closed under addition where you have a scalar multiplication, but you don't necessarily have a vector multiplication, right? So you always have vectors that have a scalar in front of it, and that'll still be a vector. It's closed under that. And a scalar just means a real number or a complex number or whatever you're using for your number field or ring, or in vector space, you have to have a field, but whatever you're using as your numbers, you have a scaling property in the vector space. Since we're talking about vector norms, there needs to be a scalar c. We have to decide what to do with that. And that's tied up in these properties here, or these axioms. So the first one is non-negativity. We already talked about that a little bit. The vector norm needs to be greater than or equal to 0, and equal to 0 if and only if it's the 0 vector. So what that means is that the vector norm length of 0 is 0, and if the vector norm length of 0 is 0, well, then the vector itself has to be 0, right? So just think about this infinity norm for a second. If the maximum absolute value of all of its components is 0, if that's the biggest one in absolute value, then they're all 0. So that means it had to be the 0 vector, right? And that's what's being encoded in this first property. Okay, the next property is homogeneity, and this is, we know that in vector spaces, if x is a vector, so is cx, right? So that's what we have the scalar c here. And that just means you have your x, whatever the norm of x is, and then that'll be the same as just multiplying by the absolute value of c. So you can think of real numbers or complex numbers, and then you would just multiply your vector x by the absolute value. So that would be the new length of x, or cx. And the final one is the triangle inequality, which is very, very useful in doing proofs and solving different kind of errors and estimates. And that just says if I take two vectors and I add them, and then I try to figure out what is the norm of those added vectors, well, that's going to be bounded by the sum of their norms. So it'll be bounded by the norm of the first one plus the norm of the second one. So that's the triangle inequality. And all vector norms, in order to be a norm, need to satisfy these properties. So you can't call it a norm if it fails one of these properties. So that's something you can check. You check different types of norms. You can check these ones that I've written here and see if they satisfy those properties. Maybe I made a mistake, but you can check for yourselves and see if they satisfy. And then if they do satisfy these, you can feel confident and say, yes, this is a norm. Okay, so we don't have to stop with just vectors. In reality, you can think of a matrix as a vector in a certain way, but you can also take your matrices and put norms on those. So you can say, like, how big is a matrix by using this notion of a norm? And let's talk about that a little bit. A matrix norm denoted double bracket A, capital A. Notice I'm using small for vectors, small letters for vectors, capitals for matrices, where A is a matrix. This is a function that maps a matrix to a non-negative real number. Same idea as the vector norm. And there's also various matrix norms. One of the most common is the induced norm, which is based on vector norms. And the idea here is the induced, for example, the induced 2 norm of a matrix is defined as, double A 2. Well, that's going to be the max for x not equal to 0 of AX in the L2 norm. So what does that mean? So AX should be a vector if X is a vector. That's the idea we're using here. And so that means it has an L2 norm. So we take the L2 norm of this vector and then divide by the L2 norm of the vector X, right? That's what it means when it says it's based on vector norms. So these are the vector norms on the right here for all x not equal to 0. And then we have a new notation on the left here, which is the 2 norm of the matrix A. And what's cool about this, the reason that I point out specifically the 2 norm for matrix norms is that this essentially measures how much A stretches a vector when it acts on the vector. So what does it do to vectors in this 2 norm? And we'll look at some examples and see how we can think about that. Okay, so again, matrix norms have to satisfy properties similar to vector norms. So, and they're the same properties. So in reality, it's the same as vector norms. And you can take away the word matrix, and you can take away the word vector. And the idea is that any norm has to satisfy these properties, right? But since vectors are kind of this, abstract thing, there's lots of different things you can think of as vectors. So, you could think of functions as vectors even. But no matter what, if you have a norm on this space of things, these objects that you're thinking about as vectors, then you have to satisfy these properties. For us, we can think about just vectors and matrices because we're doing, numerical methods, but just understand that these can be generalized to sort of abstract objects. So again, we have the matrix norm of a matrix A has to be greater than or equal to 0. That's encoded in the definition. It has to be a non-negative function, so that's already kind of given. And then it's equal if and only if it's the 0 matrix. Right, and you can check that for this norm right here, which would be, well, actually this norm would be a little bit tricky, I guess, because you're taking x not equal to 0. But this would be, you could check it, you could run through a proof and look at it. Homogeneity, again, we have the matrix norm of C times a matrix, right? So that would just be multiplying the entries of A by C, because matrices are a vector space over some, field of scalars. That'll just be the absolute value of C times whatever the matrix norm of A was. And finally, we have the triangle inequality. Remember that we can add matrices and then take the norm of the two added matrices, and that has to be bounded by the sum of the norms of the two matrices. And the little caveat here is that the matrices A and B need to be the same size, right? Why? Because you can't add matrices of different size. So that's what you get there. I want to say a little bit about matrices as a normed vector space. So if you have a vector space and it has a norm, then you can call it a normed vector space. Remarkably, which is pretty cool, matrices themselves form a normed vector space, right? So I showed you that, or we know from linear algebra that matrices are a vector space, and then I've shown you here that there's a norm that you can put on that. So when you have the set of matrices, you have a normed vector space. This means that matrices can be treated as mathematical objects with a size or magnitude, right? And that's going to come in handy when we're trying to do real world problems and looking at different things using numerical methods. So it's a good thing to know. Okay, that was a lot. Let me just stop there and see if we have any questions. Okay, nothing in the chat. So I assume everybody is following along okay. I assume I'm not going too fast or anything. Like I said, if so, let me know and I can slow down, re-explain, whatever you guys need. All right, so now that we've talked about these norms, let's look at some different examples. So these aren't too fancy, but I will show you a couple of interesting examples. The first one is just a basic example on how we can actually find a norm. So in this case, I'm going to use from the NumPy library just the linear algebra norm, and that'll be the 2 norm of a matrix, the one we just talked about. So what I've done here is I've defined a matrix, and that's just an array, and then the first row would be 1, 2. The second row would be 3, 4. That gives me a way to create a matrix using Python and in particular NumPy, which is just a numerical library in Python that we can use. And the matrix norm then would be to just use the norm function of A, and we find the linear algebra norm. So you could calculate this yourself, and I'll go ahead and print the matrix A, and then we'll print the 2 norm of A. So, all right, so there's our matrix A. We know that it had rows 1, 2, 3, 4, and then we found the 2 norm, and it's just this number. So remember, it's a non-negative number. So this is a way to say how big A actually is. Okay. Okay, so this is a little bit more interesting example. So again, we can use the 2 norm, the induced 2 norm. And I have my matrix here, 3, 1, 1, 2, same way as I made it before. And then I wanted to find a unit circle. And then what I'm going to do is show you like how the norm of A can transform and stretch the unit circle and how we can kind of look at that. So to get an idea of what's going on with vectors. I define a variable theta, which is going to be my angles, and that'll be just 100 values between 0 and 2 pi using this mp.linspace function. And then to create the unit circle, I simply just apply cosine sine, right? So I have a two-dimensional vector here of values, a bunch of values, and the cosine of theta, the sine of theta. And as everybody knows, you know, you can parameterize a circle every point on a circle x, y by cosine and sine. So that's from, you know, your algebra classes. The next thing we want to do is apply the matrix A. So we want to see what happens if I take all the vectors on that circle and then just multiply those one by A and see what that does to that shape, right? So this will be our transformed circle. And all I'm doing is this dot product, which is matrix multiplication, taking my matrix A and multiplying it by every single vector in this list, all 100 of them. And then that's going to give me a new transformed circle to understand, you know, what is the norm of my matrix A and what does that norm mean when it's transforming this circle. And to get the norm, I just calculate the 2 norm of A. So I should have an order 2 here. I think I forgot the order 2 up here. Yes. So that would be the 2 norm. Otherwise, it's just the regular norm. Pretty close, anyway. So I have my order 2 here, and then I want to plot my circles. So I'm just using a basic plotting function, plotting library actually called matplotlib, defining how big I want my pictures to be and what to plot. So I'm using my first unit circle, my second unit circle, that'll be my basic unit circle. And then for my second plot, I'm using my transformed circle after I multiplied every point in my first unit circle by A to get my transformed circle. And then I'm going to output what the 2 norm of A is. So let's go ahead and take a look at this and see what we get. Okay, so as you can see, I had a perfect circle here on the left. So that was my, and then I multiplied it by that matrix A, who has a norm of 3.62. And there was some stretching involved. And now I have more of an ellipse here on the right. So understanding the norm and what it does on these circles and the norm of A, it gives us an indication of what's going to happen to vectors if we apply vectors in the plane, right? And by thinking of it in terms of that and understanding the norms, you can design algorithms a little bit better and sort of understand what's happening. For example, if you're going to do like a neural network, right? That's just a whole bunch of matrix multiplications, basically. And you could get from the norms of those matrices, you could start understanding what they're vectors and then how to better approximate that by, you know, tuning your parameters a little bit. So this is not a useless piece of information. It actually has some practical implications. Okay. So I just want to talk about that a little bit here. So in the example, I explored the concept of the induced 2 norm of a square matrix A and visualized how does it affect vectors, and using the unit circle as an example. So you'll see if you continue in mathematics, the unit circle or the unit ball is often a very good starting place to understand things about the way your functions are working, or especially the norms of your functions. And when you get deeper, it has some really strong implications about what you can do, especially about things like compactness and finite, which is sort of a generalization of finiteness. In the example, we defined the unit circle in the 2D plane. And, that's just the regular unit circle. You probably know this definition, I'm sure. Every point is a fixed distance of 1 unit from the origin. Mathematically, we represented it parametrically as cosine theta sine theta, which I'm sure you've seen in calculus classes, this parametric representations. So the idea was to understand how it affects vectors applied on the unit circle. We saw that with the ellipse. And then we used the induced 2 norm of the square matrix as a measure of how it stretches vectors when it acts on them. And this is just the definition again, just to kind of drive it home into your brain. And we calculated this 2 norm of the matrix using this formula here. Yeah, this is just how I did the visualization. I already talked through it, but we generate points on the unit circle using the parametric equations, apply A to these points, transforming them, and then the second plot shows the transformed circle, illustrating how each point on the circle has moved. And the title of the second plot is the induced 2 norm, indicating the maximum stretching factor. And the transformations helps us to understand how matrices affect vectors and how the 2 norm quantifies this effect. All right, so just to give you one last look at it, you can see that this number here is really telling us how our vectors are being stretched. Okay. All right, let's see if there's any questions before we go on to this. Okay, so far so good. Okay, I just wanted to give you a real world example of where you might use vector norms, in the real world. And, there's a lot of obvious things that we talk about using, machine learning and all that, but I wanted to do something a little bit, not so much because we're going to do so many algorithms and things in this class. It's good to understand that these ideas show up around you in other areas as well. And then maybe you can creatively, use these to do different things. So suppose you're a financial analyst working for an investment firm, and you've been given the task of assessing the diversification of a client's stock portfolio. So the client has invested in a set of N different stocks, and you need to determine how diverse the portfolio is. So to assess this diversification, you can use the Euclidean norm or the L2 norm of the portfolio's returns. Now this is the Euclidean norm. So I have a vector x, x1, x2, all the way up to xn. Then I have my notation here on the left for the 2 norm. And remember, that was the square root, or in this case, it would be 1 over 2, 1/2, right? As we saw in the other definition. And then underneath that square root, or within those parentheses, taken to the power 1/2, we have the sum of the squares of each component of the vector, x1 squared plus x2 squared, etc. However, in this problem, each xi is the ith stock of the portfolio. And you want to write a Python program that does the following, right? So you want to take as input the returns of the N stocks of the portfolio. 2, we want to calculate the Euclidean norm of the portfolio's returns, and that'll tell us how diverse it is. And then 3, we'll create a diversification score, right? So as you can imagine, you can use this idea of creating a score in the same way that we've been doing, which is just a thresholding idea for different numerical algorithms. This is also a numerical algorithm, right? So if the 2 norm is less than the threshold for some predefined value, we consider the portfolio well diversified. If it's greater or equal to the threshold, the portfolio is poorly diversified. Okay, and then finally we want to output the diversification assessment and the Euclidean norm. All right, so here's our portfolio returns, right? We have these different stocks. These are the returns that we're getting. So a 3% return, 2%, 4%. This one's not doing great. It has a negative return. And this one just has a 5% return. and our threshold for that would be 0.05, right? And if you actually check, I'll let you do this kind of on your own. It's a pretty easy exercise. You can use your calculator or whatever. The Euclidean norm of returns is 0.06, or if we round that, 0.7, and that's going to be, oh yeah, these are not right. Okay, so, but we'll consider this to be pretty well diversified because it's higher than the threshold that we have. So we're getting on average kind of a norm of a 6 or 7%. So that's pretty good. All right, so that I just wanted to introduce that to you so that you could see a real world example kind of simply of how you might use norms, right? Other than just like determining more how big a matrix is, and to realize that there's some motivation behind these ideas. All right, let me check the chat again. Going good. All right. Okay, so let's go ahead and finish a couple of more iterative methods for solving linear systems. So we already talked about some different iterative methods. We talked about the bisection method, and we talked about the fixed point method. And these are a little bit more geared towards numerical methods. So there's another way that we can solve systems of linear equations using iterative methods. So just to give you a recap, iterative methods are a class of techniques that we can use to solve systems of linear equations iteratively. And what we want to do is gradually improve on an initial guess to reach a solution. So two commonly used iterative methods are the Jacobi iteration and the Gauss-Seidel iteration. So I'm going to explore these methods and provide some Python examples to implement them. All right, so the Jacobi iteration method is an iterative method for solving the linear system AX equals B. Again, we have A as a square matrix and X as a vector of unknowns. B is the right-hand side vector. So again, we have a linear equation. We're given B, we're given A. This will show up a lot in the real world, these linear equations like this. And we want to solve for X. So we want to find all the X's that solve this. We've seen a few different techniques to do this, but this is the Jacobi iteration method. So how does this work? Well, we initialize an initial guess for X, right? And we'll call that X0. And for each component of X0, we'll compute the new X estimate, xk plus 1, using the following formula. Okay, so xi of xk plus 1 is going to be 1 divided by the aii, so that'll be the that'll be on the diagonal of your matrix A, right? So aii would be like A11, A22, whatever. And you see that I've indexed the ith term here and then we also have a k here in the in the exponent here. So 1 divided by aii, and in parentheses I'll take bi, right? So these i's are related, and then we're going to sum over all j's not equal to I. So in this part here, none of these terms ai and will be aii. So they'll be off of the diagonal because we want all of the j's not equal to I, and we're summing over the j, so the second index here. And then the xj as well, so x will also never be aii, or xi, I'm sorry, and the xk will be defined just in the same way as we've defined it here. So this is the algorithm that we'll use to get in order to solve our equation. And so we take the bi and we subtract from it the sum of the aij, xj, k, where j is not equal to I. And we'll repeat this until convergence is achieved or some maximum number of iterations is achieved. All right, so Yeah, so I've written a little code here. Let me just go through it. Okay, so for this code, I have NumPy that I'm using, the numerical library in Python. And I've created a function called Jacobi iteration because it is the Jacobi iteration method. And so this function, it takes as input a square matrix A, a vector B that you want to find the solution. That's your solution, AX equals B, an initial guess, a tolerance, and then some max number of iterations. So, and it's going to repeat the method that we used above until we find the tolerance or the max iterations is reached. Okay, so n will be the length of B. So we used before n to be the length of A0, which was like the first dimension of 0. But since n is a square matrix, B must have the same length as n. So you can also just use the length of B. And then I'm going to, just to avoid maybe any errors that I might see, and I'm going to make a copy of the initial guess. Okay, so that'll be my x. And my goal is to determine which x's have the property ax equal to b. So my goal is to find x. All right, so that's our initial starting point. Now I have a for loop, a couple of nested for loops actually, and for each iteration in the range of max iterations. So in this case, max iterations is 100. So for each iteration in range 100, so it starts at 0 and go up to 99. In Python, if you're using R, it maybe starts at 1. But for each one of those, I'll use this iteration, and this for loop will go through there and just index each one of these. So my x new will be I'm just going to initialize it with a vector of zeros of length n. So that just gives me basically a vector of n entries, and they're all 0. So I start with my iteration, I start with my x new, and now I start a new for loop, right? So n's defined up here for I in range n, right? Now I want to create the entries for my x vector, right? I know my x vector has to also be of size n because A is an n by n matrix and B is of size n by 1. So also there must be n entries in x. So that's what I'm looking to find here. And here you see I've just used the formula above. So I take my BI, so it'll start with B0, and then I'm going to subtract from that these dot products of AI and XI, right? So AI, XJ, and in this case, since there's just one for each copy, I'm not summing over all of them yet. I'm just searching for the solution to the problem. So BI minus this multiplication here, and then minus the multiplication of the last ones. So that's the same as summing, right? Since these are all negative, AIJ, XJ is minus that, and then we subtract the other one as well. And then I'm just going to go that and go through all of the I in range n. So this is basically taking care of the sum here, even though you don't see a sum in the formula here. But we're subtracting, 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 which is what's going on up here. So if you think about that for a minute, you'll realize that makes sense. And then we're going to divide by AII, right? So that was the last piece, to divide by AII. All right, and then if the norm of the new minus the original x is less than the tolerance, then I'll return whatever my value is, and then I'll add 1 to my iteration, right? And then it's going to just iterate through all of those, give us what we want, and then when I'll say x will be the new copy, and I'll return x, and in this case the max iterations. And to implement this, you can see what I've done here is created an array, just a 3 by 3. 412 is the first row, second row is 351, last row is 113. And then for my matrix that I'm trying to find ax equals b, my b solution vector is going to be another array, just 4, 7, 3. And for the initial guess, I've just started out with 0, 0, 0, and I'm going to apply the Jacobi iteration function. That's going to give me the solution x, as you can see here, and then it's going to tell me how many iterations it took to get x. And the reason that I care about that is because I care about the convergence of my algorithms. So I want to keep track of my tolerance, my number of iterations, and see how well the algorithm's doing. I want to print the solution, and I want to print the iterations. So basically, that's just this code here being implemented. We can run this cell and see what we get. Let's see. All right, so it solved it after 49 iterations. I didn't need to use all 100. And it's claiming that the vector that I get is 0.5, 1, 0.5. That should give us, if we check, let's see. Well, there's going to have to be. Okay, so I'll let you guys check that if you want. But that should give us, if we take A times this vector in the right order, I'd have to transform it a little bit, so I don't want to take the time to do that. But that should give us our B vector here. So that's one thing that we can do to solve this system of equations using this new technique, this Jacobi iteration technique. All right, so that's that one. Okay, let's go ahead and talk about one last iteration method. This is called the Gauss-Seidel iteration method. So the Gauss-Seidel iteration is another iterative method for solving linear equations of the form ax equals b. Again, A is a square matrix, x is the vector of unknowns, and b is the right-hand side solution vector. So this is a little bit of an improvement over the Jacobi iteration method because it uses the updated value of x as soon as it becomes available within each iteration. So you don't necessarily have to wait for further iterations to update your value of x. We can use it immediately. Okay, and the algorithm for this is exactly as follows. We start with an initial guess for x. We'll call that x superscript 0. And so this is a vector. Remember, x is a vector, so this is denoting a vector. That's why it doesn't have double scripting like that. The double scripting, if I didn't say, is the components of the vector, right? x1, x2, xn. And in this case, x0 is the vector. We need to do that in order to have some kind of notation for this algorithm, and that's the best notation that works. So it might take a little bit longer to wrap your head around the notation, but that's what's going on. For each component of x0, we'll compute the new estimate for xk plus 1 using this formula, right? So xi of xk plus 1, so the ith component of xk plus 1 is going to follow this formula, right? And again, you can see that it's similar to the previous formula, but not exactly the same, right? So we divide by aii, so the ith component on the diagonal of A. We take bi and we subtract. Now for j less than I, aij xj to the k plus 1, right? And then minus for j greater than ai, aij xj to the k. And in this case, we will just keep repeating the step again until we find convergence or we reach the maximum number of iterations. And so let me just take a quick moment to talk about that. So in numerical methods, oftentimes when we're doing these algorithms, there's two ways to know, when the algorithm converges. Either you're going to let it run for some really, really long time until you run through all of the iterations and you're just like, okay, this is too costly for the computer. It's not worth it. Maybe I should reassess and look at another algorithm, or you let it run until it reaches some tolerance, less than some, tolerance that you're okay with how accurate it is computing whatever value you're trying to compute. So often you'll see these two things going hand in hand, which is the maximum number of iterations, which is how long you let the computer run basically until you decide that this is not worth using this algorithm, or this tolerance, which is what you want, which is saying that this algorithm is converging and it's very, very close to the actual solution. So that's kind of the game that you play when you're doing a lot of these numerical methods. So the method is really useful when A is diagonally dominant. So what does that mean? It means that the diagonal elements of A are larger in absolute value than the sum of the absolute values of the off diagonal elements in each row. So let's just like kind of pick that apart for a second. So we have the diagonal elements of A, and we know that those are larger in absolute value, right, than the sum of the absolute values of everything that's not on the diagonal. And then that would be diagonally dominant, right? So when you have a matrix like that, you can think, oh, okay, that's a good time to use the Gauss-Seidel iteration method, right? Because these diagonal ones are way bigger than the sum of the ones not on the diagonal. So that's one little rule of thumb that you can use when to apply this. All right, so I just want to kind of look at this mathematically. I know it's a lot of notation. There's a lot of I's and J's and K's, and it can be very confusing. I remember when I was a student, and all of this notation was really kind of difficult. So I just want to take some time and reiterate on this to give you a better feel for it. So here's our formula: the xi, the k plus 1. So that would be the ith component of the k plus 1 vector. It has equal to 1 over aii, right? Bi minus the sum for j less than I. So we're summing on the j's of aij times xj k plus 1, right? And here you can see that we're updating as we go. And we subtract for the j's greater than I of aij xj to the k. Okay, and here we have xi to the k plus 1 is the updated value of the ith component of x in the k plus 1 iteration. So we're getting a vector every time, and it'll be like x0 with superscripts, right? x0, x1, x2, all the way up to xk plus 1. And for each one of those vectors, they have elements or components in the vector, like a vector like 1, 2, 3, right? So what this is saying is this is the ith component. Like if it was the first component, you could say 1 for 1, 2, 3, and of the k plus 1 iteration. So that's what that's saying. So it's the updated value of the ith component of x in the k plus first iteration. aii is the diagonal element of A in the ith row or ith column. So I think that's pretty easy, clear for you. Bi is the ith component of the right-hand side vector of B. I think that should be pretty clear too. B is a vector. It's indexed by 1, 2, 3, 4, all the way up to n. So one of those is Bi. So, if it was the fourth one, it would be 4 for the vector I just said. If it was the first one, it would be 1. So B1, 1, B4 would be 4. So Bi is the ith component of the vector. Xj k plus 1. This is the updated values of the components for x for j less than I in the k plus 1 iteration, right? So these are the updated ones. And then xj to the k. So here's k plus 1, here's k. That's the values of the components for x in the j greater than I in the kth iteration. Okay, so hopefully that helps going through that notation a little bit and sort of understanding this Gauss-Seidel iteration a little bit more. So let's, I don't know, I'll leave that on there just for a second so that you can kind of absorb it. All right, so here's a Python code that I wrote to implement this Gauss-Seidel iteration, and we want to solve AX equals B. I'll go through this and talk through it with you. Again, I'm just using the NumPy library, which is the numerical library that is very useful in Python. And I've created a function here called Gauss-Seidel iteration. And this takes as a matrix A, it takes as a solution vector B. We have our initial guess, our tolerance, and our max iterations. This is really similar to the Jacobi one that I did. So just keep that in mind. So we have N is the length of B, X is the initial guess, copy of that. We're going to do nested for loops as well. And we're going to have for I in range N, which is the length of B, our xith value will be Bi minus the multiplication of Aii xi minus the I plus 1, and then we'll divide that whole thing by Aii. And then if the norm is less than the tolerance, we'll return x and iteration plus 1. Otherwise, we'll return x and the maximum iterations. Okay, so for this example, we have a 3x3 again. 412 is the first row, 351 is the second row, and the last row is 113. I've just put an extra thing here to let you know this is a data type float. That way it'll be fine with the calculations and the values. There's different data types you can use, and if you're wanting to do different kinds of calculations, you need to choose the correct data type. And also there's different precisions on the computer for each of the data types. Usually you want to stick around with float or sometimes int for your data types. I just wanted to point that out. And the point here is that when I go to multiply things, there might be, if I just made these all integers and then I wanted to multiply by like 0.5, I could get an error because it wouldn't be an integer, right? So it's good to specify what data types you want to use when you're doing these algorithms. For my solution vector B, I'm going to also make sure it's float. That's just going to be 473. I'm going to plug that in. And then again, my initial guess, but this time it's a float, will just be the 0 vector. So that's what I'll start with. And these will be the things that I plug into my Gauss-Seidel iteration function. So my matrix, my solution vector, and my initial guess. And that'll produce my solution and how many iterations it took to get the solution. And then I just print the Gauss-Seidel iteration solution, my solution, and the number of iterations as my iteration. So let's go ahead and run this, see what we get. All right, so I get a solution here of 0.5, 0.999, 0.5. So a little bit different than what we got with the Jacobi method. Numbers just a little bit off in precision, and it probably has a lot to do with the fact that I'm using a float. And in this case, it took 10 iterations to get the solution. All right, so what did we get before? Yeah, so this one took 49 iterations, right, for the Jacobi iteration. And it gave us, I'm using the same, 412, 351, 113. You can see down here, I also have 412, 351, 113. And then for my B vector, I have 473. And again, up here, I also have 473. But in this case, it took 49 iterations to get to this solution. And for the Gauss-Seidel, it took just 10 iterations to get to almost the same solution, off by just decimal places. And it could even just be, machine precision rounding error. But the important thing is that we have the algorithms here. You can use these algorithms and implement them yourself. I'll give you the notes for these algorithms and all that so that you can write this out in your own computer language. I think it's important that you learn how to code these things if you want to really learn this stuff. So I'll make sure to give you that. So let me go ahead and pause there and see if there's any questions in the chat. Okay, so I do have a couple of questions here. Great. Do we students have to master coding these Python stuff? You don't have to master it. You know, it really depends on your goals. So you will have some questions that will ask you to implement some of these algorithms. You don't have to use the same algorithms I use. I think, you know, I could just give you these algorithms, but I think you're going to learn it a lot more deeply if you learn how to actually type out the algorithm yourself, or like, you know, do a little bit of research and find some that you want to use and just kind of go through it. I think it's important that you do learn how to use the algorithms and write them out. And do you have to master them? I'd say it really depends on your goals. Okay, we have a question. Let's see. Let's see, how do I get to that? Can you type your question in the chat? There's kind of, hold on, let me see. Maybe I can do this. Oh, I see, I can open the queue. Well, you'll have to learn these formulas to answer, let's see, okay. Yeah, I can send some exercises to where you'll have to use the formulas to solve the exercises. You don't have to learn all of these, right? Like I've shown you several formulas for how to find the zeros of a function. You can implement individual ones, or you might just have a question on, you know, implementing one of the formulas or choose a formula. But yeah, there will be some questions. You'll definitely have to learn the basic idea behind these formulas. And as you know, it really depends on your goals if you want to master these things. Like, you can learn the formula to solve the problems for this class, but if you plan on doing like things like engineering at a higher level, you're going to have to know this stuff like by heart, because what you end up running into is that some problems will require you to use the correct algorithm for that problem, and you need to know which algorithms work best for which types of problems. And that's really the heart of this class, is understanding this error and this convergence, and that way, and these max iterations, so that you can choose the right algorithm to use. Yeah, I'll send some questions to Mrs. Ha. So yeah, you can definitely look at those questions and get some practice with these algorithms. And I send some notes to her as well that go through what the algorithms are, how you implement them. I would suggest that you learn a few of the algorithms and then try to implement them in whatever computer programming language you want to use. If your goal is to, you know, go further, then you might want to learn all of them, you know, by heart. It just really depends on your goals for mastery or not. So that, you know, but yeah, I'm definitely send some notes and some problems for you to work with this to Mrs. Ha. So you should be getting those in some way. If you want to like look at the ones at some of the, if you want to look at a specific algorithm in more depth, just let me know and we can go into that a little bit more. But in general, the problems for the class will be to solve a problem, you know, using an algorithm of your choice. So maybe, you know, find the zeros, and then you can use like a fixed point method, or you could use, you know, a bisection method or whatever. But yeah, I do understand that some of these, like with all of this notation and stuff, get really involved. But the important thing is that you understand, how to implement the algorithm, look at how well it's doing. Like we saw with the Gauss-Seidel, it took way less iterations than the Jacobi one, and I gave you if you see a diagonally dominant matrix, then you might want to implement this, so those are the important things, is knowing which one to use and which one would be the best one for a problem, because you don't want to have a really, really large data set that you're trying to solve, and then it's taking, like a week for the algorithm to converge. You might want to choose a different algorithm, or you may want to convert the data set into a different type of matrix, like a diagonally dominant matrix or a tridiagonal or something. And we'll have like little rules of thumb, which algorithm to use for those types of matrices. So it's not so much that you have to learn every single algorithm. You do need to know them by name and to know like when to use which, and you need to know when you should try a different algorithm, right? So if you chose like the Jacobi iteration method and it wasn't working for you to solve your problem, then at least you know now that there's also the Gauss-Seidel, right? So maybe the Jacobi's not the one you want, you can try Gauss-Seidel. That's really how this stuff works in the real world. As far as this class, I'll ask you to use some specifically, and others I'll let you choose. But I think it would be good if you get an idea for the basic techniques that are being used and how to use those techniques. And no, nobody's behind me. It's just a background screen because I don't want you to see how messy my room is. So yeah, there's nobody behind me. Okay, any other questions? All right, if there's no other questions, I'll make sure to send some practice problems to the other co-teacher, and she'll get those to you. I'll definitely send her the notes over how you actually write out the algorithms, and you can get some work practicing with that. Oh yeah, there is my cat, yeah. Yeah, definitely. All right,